Thank you, Professor Gonzalez, for inviting me. It's been a great treat to visit your beautiful campus and spend some time with the different faculty and students, understanding all of the interesting work going on here at ITAM. So I was hoping to spend some time with you today to share a little bit about what we're working on at Virginia Tech and with our international collaborators. It's a very exciting time to be in graphics, and certainly with the speeds of machines increasing, the speeds of networking increasing, we see lots and lots of opportunity to kind of change the game a little bit. And so what I'm going to try to do today is also maybe a first, but I'm going to do this presentation all in X3D, and I hope that I'll give a chance to explain kind of my approach to this problem and how I characterize the challenges of big data, which is a nice buzzword these days. But of course, big data is always just something that's bigger than what you have, right? There's no absolute measure of what is big data. It's something that's challenging. And same with supercomputers, right? They're really just defined not by the teraflops that they have, but by the work that they can get done and that you can't do on a single machine. So all of these opportunities sort of give us a chance to, give us a chance to really look at this challenge of that Donald Norman has characterized as the gulfs of evaluation and the gulfs of execution. So I know I'm really excited I get to open for Donald Norman. This is like a big highlight for me. And I think what I'll do is just kind of start off. I've built a little world here, which is a little bit of a concept map, a mind map. And we're going to go through and visit some of these different planets, if you will, that each kind of encapsulates a little piece of my work, and I think a lesson that we can carry forward. There's a lot of opportunity in virtual environments, and I'll start the talk here a little bit introducing me and where I come from. So this building that we have in the background here is our new Institute for Creativity, Arts and Technology. It's our 7th actual research institute at Virginia Tech. And we have some really unique facilities here, some that have given us a chance to investigate these different problems. And maybe if we go down here, that. This is sort of a joke, but sort of not. What's the outline of this talk? Well, we'll see. It's going to have a beginning, and it'll have a middle, and it'll have an end. So that's basically all I'm going to guarantee at this point. From Virginia Tech, you can kind of see we have a very funny, I think, history. But our mascot is the turkey. Okay, this is back in the old football days. It was a real live turkey. And then it was sort of this schematic turkey here, and now it's kind of this super turkey, which we call a hokey bird. Okay? But Virginia Tech has been growing a lot recently, and our new facilities here at the Institute for Creativity, Arts and Technology is a good sign of that. And I want to describe some of that work that's going on. So I'm coming from the Department of Computer Science. And I encourage you to troll through and see the kind of work that we're doing there on the website. But you'll notice that there's a lot of images there that are doing some visual communication about that work. So here's a good example, one that I can show in our immersive cave, which is, I'll describe a little bit more in detail. But this is in my lab in the Visionarium. And take that same data and get it to a mobile phone or a desktop. And not to have to change the data at all, or change the file, or recompile, anything, is basically looking at what's the common denominator across these platforms that lets us really do work, lets us get something done, like put pixels on the screen. Computer science department has been a great home. We also have a center for human-computer interaction, and we have a good website here. This is a really neat collection of faculty. It includes people from the history department, from our School of Visual Arts, as well as psychology, sociology, computer science, and we really get a lot of mileage out of bringing those different perspectives together. So the Center for HCI is something I encourage you to explore. Here's the Institute for Creativity, Arts, and Technology. There's the website. And the Visionarium, which is my lab. So I think what I'll do at this point is kind of jump us to a video. But you can see the Visionarium, the whole idea here is apparent in the name, maybe. It's like a planetarium or an aquarium. It's somewhere where you go to see things you can't see at home. Okay? So we have some really high-end, immersive virtual reality installations, all the way down to kind of commodity hardware game, sort of controllers, game hardware. And what we are trying to do is to study the value of these different displays. I mean, this looks really impressive, but does it actually help us to solve some problems or get some work done, right? It's a great stop for all of the VIP tours. Well, what about science? What about design, right? And why would this kind of display platform be better than something like this? So this is what I'm going to describe to you today, is how I structure this problem in looking at this huge range of devices. How can we approach this in a scientific way? And to give you a flavor of the lab, I think I can play this video. I'll play this one first. So this is the Viz Cube, which is basically a caved style system. As you'll see, we have projection coming from behind each of these screens and then down onto the floor. It's stereographic, so that means that if we put this pair of glasses on, we can actually see the structures of the molecules or the content really coming out of the screens and existing with us in the middle of the space. Okay. What we see in my lab also is, as a serving the university community, we get data, all kinds of data. And this is another thing I hope that we'll be able to appreciate. Geospatial 3D city models, to biochemistry, gene queries and chemistry simulations. What is common amongst those? Can I actually say for a biochemist why we should spend some time working on the Viz Cube when maybe they can do everything on their desktop? And I think that's the question. So this is all
perceived parties that sufficiently advanced technology will be ultimately indistinguishable from magic, and that's ultimately what you'll see with the cloud. My name is Wu Feng. I am a professor of computer science at Virginia Tech. My research is in efficient, parallel, and distributed computing, and making it easy for people to use computing resources. I started to realize that we can use computing to empower cancer researchers to help find a cure for cancer. The big thing that the cloud enables is access to computing capability that you might not otherwise have. By taking what they're doing in the wet lab and effectively digitizing that process, we'll be able to accelerate our ability to identify a cure for cancer. It wasn't too long ago, it would take 2 weeks to sequence and analyze a genome. Now, they do tens or 100 genomes per day. The cost to sequence a genome has dropped from $95 million to about $6,000. What the cloud promises is our ability to accelerate discovery and innovation. whatever I can do to help compute a cure for cancer, that's what I'd like to do.
So that was a great project, and I want to maybe just describe a little bit of some of the things that you saw in that video. So here is a network visualization program that we've developed, which we've used for a number of different kinds of domains. One of them is ontologies. Okay, this is an approach to knowledge management where we can basically define classes of things and relationships and hopefully do some computing and reasoning over them. Okay, they're notoriously hard to debug. Or to understand, if the right things are connected to the right concepts. So we made them visual. We gave a number of 3D layout techniques through the tool that we wrote for the National Science Foundation. That was the first thing. Then we saw a
the first. Yeah, that.
Oh, really? Okay, so the ITAM guest not down here?
Yeah, no.
It was good that it worked the first time. We saw the cave, right? Same data. We saw working on a connect, right? Someone interactively using some embodied interaction to work with the data. And I think this is a good example, again, of where we have some specific scientific problem, right? How can we get that scientist more insight, right? More decision-making power, more understanding of their data. And when the data gets bigger and bigger, this gets harder and harder. So I will close this out and go back to our world. The Visionarium Lab is pretty much dedicated to that kind of research. Can we make the human-computer interaction loop more efficient? So I mentioned Norman and his gulfs. He really set out the nature of the problem many years ago, and it's had a lot of mileage. Okay, so let's just see what we're looking at here. Obviously there's the human, there's some computer data over here, and there's a big space in the middle, a gulf, some kind of distance. And we need to cross that with our computer tools, right? And it happens in some straightforward steps. We first have to understand what we see with perception, right? We need to interpret that data, maybe the context of it, and then make sense of it. Okay, so I'm trying to evaluate what the computer is telling me. That's Don Norman's gulf of evaluation. Now I say, okay, well, I do want to query that gene sequence. I have a task goal. How do I do that with my computer? Well, maybe if I'm using a Connect, I do one thing. If I do it with a mouse and a menu, I'm doing something else. But I have to execute that, right? And so that's what the system sees. We have our displays and we have our interaction devices. Now, I think there's something really interesting here, and this is what I'm going to present to you today, which is something about how can we characterize the ways across these gulfs, right? It's a connection. It's somehow a network connection between the mind and the machine. All right, so here's the human, again, on the one side, and the computer on the other side. And through interaction, right, we can move information across these gulfs. So one of the things that we might have is a small phone, right, which only has so many pixels. And so I only have so much information I can get from that device, right? I would call that small bandwidth. Now if I have a lot of pixels, like in the VizCube, I have more bandwidth. I can show more information. Right? If I put it into stereo, I'm actually increasing the amount of information I'm displaying to the user. So I'm trying to cast this as a challenge of bandwidth and throughput. The throughput really being the thing that is what we're doing with how we get work done, right? So it's somehow over time. Now let's look at some ideas about this. When we have lots of senses, there's a lot of ways to get information into the brain, okay? Visual is our highest bandwidth sense, but there's a lot of other ones that we get information from too, right? Auditory information, frequency, amplitude, location. We even have good location capabilities with our auditory, and other senses that seem a little like science fiction now, but maybe are not so much. Haptic interactions are things that are happening today with surgeons training on inoperable cases and being able to operate on them successfully, right? Because they've practiced and trained with a haptic device. There's smell-o-vision. Okay, that was a really fun thing. The groups out of Asia have been doing a lot of research into olfaction and the bandwidth of that, right? How many scents can people identify, for example, is one way to measure the bandwidth of the olfactory sense. So this is how I'm trying to characterize the problem, is that we have a channel, the visual channel, and we're trying to get as much information across as we can, right? More pixels will let us do that, but we always know that, more information is not always better. It can easily become overloaded. So bandwidth is not the end-all, be-all, and the goal, I would say, in this research. But here's that idea of the bandwidth, right? If I have 1, 2, 3, 4 screens that are 1920 pixels on each side, right? That's a lot of pixels. It's a lot of bandwidth. And when we upgrade our projection system in 2 weeks, the bandwidth will be even higher. I'll talk about that. But what really is the thing that HCI, I think, can tackle is the idea of throughput. So we know that there's this carrying capacity, but how much actually moves across those gulfs, right? And this really happens to come down to the major challenges of usability. Okay, so if I think about the throughput of that connection, I'll demonstrate to you how visual displays can change the throughput, and also about how user interfaces can change the throughput. Okay, by somehow being more natural or supporting better performance. So let's talk about the throughput a little bit, and just say, okay, we're working on the same screen. We've got a fixed bandwidth right here. Okay, now if I put this table up and I asked you to tell me the relationship between income and education, right, or which state has the highest income, you would spend a lot of time reading through this spreadsheet trying to answer those questions, right? Now with the same bandwidth, I can increase the throughput by showing it as a graph. Well, immediately I can answer those questions. Yeah, it's a linear proportional relationship. There's some outliers here, and the state with the highest income, for example, is very apparent. And that's the flavor of what I'm trying to say. When we do visual displays, visualization, we're actually trying to improve the throughput. And what is happening there is mostly because a lot of those things are pre-attentive, that is, they happen before you're conscious of them. Let's look at some more examples. Okay? One of these things is not like the other. Okay? And this is what's called the pop-out effect. Okay? So I can immediately identify the one of these things that's not like the other. And I don't have to visually, serially scan and search through this data. It's pre-attentive, right? You didn't have to think about it. And that's one of the key things that I'm trying to do with my research, is to understand perception in such a way that we can use it to increase the throughput. Okay, so here's another good example. Which one is greater than the other, right? Put these chips in order. Okay? Well, that's immediately the natural ordering, right? Grayscale, pre-attentive ordering. How about this one? Put these chips in order. You have to think about it. And in fact, if you didn't have a legend, you would spend a lot of time thinking about it. Okay, so now, using a rainbow color map, we've reduced our throughput significantly, okay, just by a choice of coloring these chips. These have real impacts on user performance. There's other challenges, right? One of the things that we see a lot in engineering is people using the rainbow color scale, even though we have now nearly dozens of publications that say why that's a bad idea. Okay? And it's bad for a couple of reasons. It's not perceptually linear, right? I showed you here. It's arbitrary, the order. Okay? Oh yeah, I know the rainbow scheme, Roy G. Biv, thinking about it. That's arbitrary though, right? It was a conscious decision. So it's not perceptually linear, whereas in grayscale we do know pre-attentively a value is higher or lower than another. So it's not pre-attentive, yet people are still using it. We also notice that because of the physiology of the eye, right, this is something that we all share, the rainbow and color sequences lose all sorts of spatial data. Okay, you see in this is the same data, left and right, same data, but here's with a grayscale color map, here's with our rainbow color map. Right, all of these features up here are washed out. And why is that? I'm sorry, I guess I'll have to explain it here. Well, we have, in our eyes, we have rods and cones. These are our phototransducers. We have 3 times as many cones than we do, rods than cones. Which means that if you're trying to detect the difference between 2 pixels, right, you are able to do that 3 times the accuracy in a grayscale image than in a color image. Okay, this has practical implications too. So people have made journal papers and publishing a figure, and oh, we forgot, the journal doesn't do color. Right? Well, I only made my figure at 300 dots per inch, right? Which is a good resolution for a color picture. Basically, photos about 300. You can't tell much beyond that. But you're going to need 600 or 900 dots per inch to make a grayscale image not look grainy, right? And it's just because of the way the eye is built. 3 times the accuracy. And this is also, incidentally, why we have X-rays are still in grayscale, because you can see small differences. That's a tumor, right? That's important to be able to distinguish these fine values. Okay? So same screen, but we're changing the throughput. And one of the things that when we look at what we're doing in the Visionarium is looking at how can we tune bandwidth and throughput together, because as we've seen, there's lots of different displays. And one of the things that lets us go take our same data and go to all these different displays is the ISO standard of X3D. It's a platform-independent standard. It was built basically for the web, where you don't know what device is going to connect to you, right? So you still have some very fundamental kinds of interactions, like a selection or whatnot, but that selection might be done by, a leap or a connect or a mouse, right? Each of those has different bandwidth. And when I say bandwidth for an interactive device, I'm really talking about the degrees of freedom, okay? So if I'm trying to get information from me to the computer, and I only have 2 dimensions to work with, my mouse, right, it might take a while to get all my information across there. Like, for example, where to fly, in the 3D world, right? Now, if I have maybe a 6-degree of freedom device, like a head tracker, right? I just have to look around the corner or step forward. I can get that same information, X, Y, Z, and the orientation, to the computer, right, with a higher bandwidth because I have more degrees of freedom to work with in my interface device. Okay, and this is really about the technology that enables testing across all these different kinds of bandwidths. It's at web3d.org, and I'll come back to some of these issues and really prove to you some of the value of the ISO standards, especially with regards to durability. It is adopted all over the world. There's an international community that develops these standards. There's governments that fund and support these standards. ISO standards are ratified by all the governing nations, right? They have to send a delegate and say yes or no, okay? So there's a great deal of stability there. One example that we'll come back to a little bit as well is from our National Institute of Health, where they're really working to be cross-platform and independent of whatever device you're browsing on. But they're taking something from, let's say, a laser scan or an MRI scan or a molecular simulation, and they want to 3D print it, right? We can take that same 3D file, right, and put it out to a physical object. And now actually I have a lot of degrees of freedom to interact with a physical object, right? All my fingers, for example. Or the case of the Oculus Rift, right? There's a lot of excitement and hype around VR these days, and I think that's a good thing. It means there's a lot more people trying to engineer and improve it. A lot of the issues are still the same ones that we've had for 20 years. But some things have changed, which is basically that there is a huge community around the world that is working on trying to solve these problems together and to make standards that are compatible, right? The World Wide Web Consortium, Web3D, and also trying to get that out to more people. There's a number of great hackathon events running internationally that give people a chance to play across these different bandwidths and try to increase the throughput. Okay, so before we go out of this little planet world here, I wanted to show you what we're looking at here. I might fly into this model. This is from the Smithsonian. They've been doing a large cultural heritage digitization project. And this is the example of one of their scans. You can see we have a very nice amount of detail on the carving. Well, it's hard to see in the light.
Turn up that light.
There we go. And what this means is that, right, we can now take all of those artifacts out of the basement that never see the light of day and have researchers be able to look at them, study them, annotate them, for example. And this is a great case because before this object was scanned, there was one interpretation about the carvings. It was a story of the Buddha's life. Okay? And as soon as we were able to put that out to the international community, all of a sudden there were like 5 new discoveries about what these carvings mean and how they interrelate. Okay? So it's that idea of getting the content out to the people and scaling that up. There's another example here. If I did make a little widget set here so I can, maybe move this around a little bit. If I wanted to look at different sides of it, or we'll just fast forward to the next model, which also happens to be from the Smithsonian. These are about 1.2, 1.3 million triangles. Okay, here's the Mammoth. This is a classic Smithsonian specimen. Take the headlight off, it's a little better. And I think maybe one of the things to highlight here is, again, being able to mash up all of these different data sources and distribute them to different kinds of clients. Okay, so here's our Center for the Arts. We've got this really fascinating staircase thing going on here in the front. And if you look at the ICAT website, we just did a bunch of projection mapping installation on the inside of this. It was really a beautiful, beautiful event. All right, so I'm going to fast forward here to another view. I think that must be here. Nope, keep going. What happens when I mash up all of these things is all of the different viewpoints come in to the same file. And I think I can do it over here. Okay. So this is a world that I built in 1998. Okay, when we had 14.4 modems. And 600K was a lot to render. Okay? But this is VRML. This is the ISO standard. And that's the reason why it's running today on the newest, latest graphics cards and platforms. You can tell this is kind of animation from that time. These humanoid animations where you have like sort of segments that get animated. I think in the last couple of years this has really become more of a, most of our virtual characters have seamless meshes now, sort of all mesh. But this was a world that we built to basically advertise our record label at the time. And it still runs today, which I think is the thing that's most exciting. So here's, this guy's kind of fun too. If I get close enough, I'll do a little dance for us. And I'm not showing this because I think this is a good example of, you know, state-of-the-art graphics. And it's not. It's almost 20 years old. Right? If anybody can show me a demo of 3D graphics older than 18 years, I'll buy you a beer. Okay? So this is really, and I actually have one that's maybe 19 years. I'll show you later. So it was a really fun project. We used you know, satellite imagery to make the terrain. We built the pyramids as if they were built you know, in 2500 BC or whatever it was. And of course part of our theory was that, you know, it was all inspired by aliens. You can take a magic carpet ride around the world, explore some of these other pyramids, and it's very fun. But this is all 1998. It was my first 3D world. Still running and still giving me some mileage, I have to say. Okay, so let's fast forward to the next planet. Maybe something out here. Well, before I go into this, is a more recent example. This one here, where we're really trying to use environmental monitoring and citizen science to help our ecosystem and our environment. So we have students going out monitoring our streams. They're taking 360 panorama photos, which are geo-referenced, and they're uploading those to a server where they can be shared. And let's go inside here just to kind of get a sense of what this is here. Okay, so I can look down. There's the water down here. There's the bottom of the photosphere. There's the river. But just taking the latest Google Street View data, right, which is just an image warped in a certain way. Hey, let's plaster it on the inside of a sphere. It works. It works pretty well. Okay, so the data has definitely evolved, and the platforms have too. So certainly we've seen Moore's Law helping us out a lot, you know, like a lot of times all of those memory management issues just magically go away because a new OS came out. But then there's the networks that were connecting us all. There's the fact that we can carry around a computer that is more powerful than what sent a man to the moon, right, in our pockets every day. Are we really taking advantage of that? But the technology has changed a lot, and so that's what's sort of brought about the idea of bandwidth and trying to characterize the problem as bandwidth and throughput, okay? So we've got more and more screens. We can tile them, run them from a cluster or from one machine in many cases. More pixels, a lot more brightness than we had before, and it's much more affordable. So just to give you an idea, when we first built the Virginia Tech cave, I think the NSF gave us a grant for about $1.25 million to build it. $1.25 million to build a display. And it was great because we had faculty from all over campus buying in, saying we want this, we need it. And when I just purchased the upgrade this year, which is effectively, I have to think of the factor, the number, but it's at least 10 times more bright, faster GPUs, right? It's 15 years of technology has evolved. And it looks better and it's cheaper. It's about $300,000 for the new projection system. So this is something that makes it really interesting to figure out, well, why would this kind of be a good display, right? Well, that Oculus Rift is only $350. Like, why shouldn't we just buy a bunch of those? And this is what we're talking about today. So Deep 6, this was one of the examples from that Microsoft video. Lots of different kinds of data, being able to see them all at once, kind of build a workspace, right? And we've actually done a number of studies where up to about 7 or 8 monitors, people's productivity increases. You can actually do about 27 times the work in about 3 times the time, so that's a factor of 9, yeah, on these displays as they go up without losing any accuracy. Okay? Once you get above 7 or 8 displays, other challenges start to kick in, right? I lose my mouse somewhere in this huge workspace. If I want to get from this end of the workspace to this end, I start to row. You know, just got a row over there. So the display bandwidth is really high, right, in some of these things. But we're having some challenges trying to interact with it just with the mouse. Okay. So that's our Deep 6 example. Here's the other example in Oculus Rift. One of our students is working on how do we organize workspaces when you have such a limited number of pixels to work with. Here's some of that graph data shown in our VizCube, our cave. Okay, so before we get in here, let's talk about how are these different platforms different, these last couple that we looked at. Anybody want to venture a guess of how they're different? We've seen the desktop display, we've seen the Rift, we've seen the cave. Well, this is the question that I set out to answer. So, one of the ways you can quantify the difference is just by the number of pixels, right? How much information can be pushed across the visual channel. That's the bandwidth. And I think total pixel count is probably not a good measure of bandwidth, and I'll talk about why. But first of all, we can see here's our current VizCube at Virginia Tech. Here's what will be after the upgrade. And down here, here's Deep 6. This is that other screen, 6-panel screen that we saw, it's doing pretty well in terms of the number of pixels, right? And way down here is our Oculus Rift and an HD television. Okay. So while pixel count might be a good measure, it doesn't really tell us everything, right? So if I need to try to read 100 pages of Charles Dickens, okay, maybe I want to set it up far away or nearby, my reading distance from the pages, but it actually matters how legible that information is. If I'm standing back here and my pixels are being projected on there and all my pixels are like 4 inches big, I'm only going to get 4 pages of Charles Dickens on the screen that I can actually read. But if we make a smaller pixels per visual degree, now I can actually make more information legible. Okay? So this is the idea of, you got to be able to read the stuff in the virtual environment. So here again, the new Hypercube is doing pretty well and is certainly competitive with the kind of work and reading that you do on your desktop. Okay? That's the kind of resolution, spatial resolution that we're talking about. So it's degrees of visual angle. I'm not sure about this one. It seems like it should be interesting, but the jury is still out. You know, the ratio of visible pixels to how much workspace there is. Okay, so this really comes into play with a lot of virtual reality systems, where I've got screens all on all sides of me, and I can see this much of the screen at once. That's my field of view. But if I turn, I can still see some pixels over here. If I turn here, I can see pixels. This is what's called field of regard, and I'll maybe take this chance to go past this little volume rendering and CAD tool and look at this world. So I tried to make a graphical depiction of field of regard and field of view. See, so this blue sphere that you see represents the space where there's display for an Oculus Rift, a head-mounted display. Right? So if I put the screen right in front of my face, anywhere I look, there's going to be screen. Okay? So the field of regard is like 360 degrees in both directions. Okay? Now that's the field of regard. If I'm in something like the cave, right? I don't have, in ours at Virginia Tech anyway, I don't have a back to my, or a ceiling. I've noticed something here that I should fix next time. But this guy in the middle of our display, sorry, do that again. I gotta just go right through this time. Okay. So somehow the cave has less field of regard than the Oculus Rift, right? Because if I look up, there's no screen. If I look behind me, there's no screen. Somehow it's less. But this field of regard is where our workspace is, okay? So I might collect a bunch of things that are related and set them over here on this side of my workspace. Maybe they're over here in my workspace. But I can only see so much of my workspace at a time, right? Which is the field of view. So you can kind of see this is what we call in 3D graphics the view frustum. Okay? It's the part of the world that's actually getting projected onto the screen. I'll back up here a little bit. What we've got here on the side, I should just mention since we're kind of free flying around here. This is a CAD part that we scanned with basically an X-ray machine to do non-invasive sensing. Right? You want to figure out if there's a crack in this piece of metal or something, scan it. But this is doing volume rendering in X3D, and it's right in my my web browser. If I go forward one more, I'm going to sort of give you another model that is a good challenge on the data that we're passing through. This is actually an airflow simulation where we're working on energy efficient buildings. Okay? So here we've used a supercomputer to simulate when the heat turns on, what happens? How does the air mix? And when we put this into life size, right, you can actually walk into the room and stand where your desk is and see that, oh yeah, there's a terrible downdraft here. I knew it. I can prove it to your boss now. I need a heater. But here's another example of, kind of real industrial data that we're trying to mash up and put together into this world. Okay, so we'll keep going. Let's see. I think there's a few more metrics in this slide deck. And this, by the way, is about 130 megabytes of geometry. I've compressed it down, so it's probably a little more like 60 or so megabytes. Okay. So what I need to do is get past this guy. And I've painted myself into a corner. Okay, here we go. Next. Alright, so when we think about the pixels per degree, so how much legible space is in my workspace, here we come up with another set of rankings. Okay, and then our projection-based VR is doing pretty well. Okay, but the Rift is coming up. It's actually pretty close to that 6-screen tiled display. And I think that's probably the last one. I think this is probably the best measure of bandwidth for a display. Right now it's my leading candidate. And not just because we came out on top, but it makes sense. And I think I've tried to sort of describe the logic to you, how we develop these metrics. So if we're going to do throughput, we need to have good frame rates, right? We're not going to be waiting for the next frame to come. And we've seen a lot of exciting developments in that way. So we've started, when we get large data sets like that airflow simulation, we actually use our supercomputer cluster to do the rendering. So we take that huge data set, stick it on 4 nodes, use the parallel I/O of that supercomputer to be able to suck up 38 gigabytes or 138 gigabytes or terabytes of data, right? Which you could not load in your lifetime on a serial drive. Okay, so we did some experiments on our Blue Ridge cluster, and this is kind of to give you a little bit of flavor about the throughput. And I'm going to accelerate here, but here's a structured mesh. I was talking about 28 gigabytes. We add more nodes and processors, and we get kind of a nice speed up curve. Okay, and that's the throughput of scaling rendering. An unstructured mesh. We did a similar study here. This was slightly smaller, but unstructured meshes are a bigger challenge. If you're going to try to do domain decomposition, divide up, the work among separate machines, but we're still getting a pretty nice curve there. This is just more data about the airflow simulation. Okay. Let's keep scrolling down. Okay, cool. So I am going to have to sort of fast forward to this one because I think this is we did a simulation that's from the video that you saw. It's myoglobin. Got it inside the world here. There's one more that I wanted. So here's the thing to notice about this, about throughput, right? This is a pretty complex system, but it supplies oxygen to our smooth muscles, this protein. And this is the iron atom. This is what carries the oxygen, binds with it. But if you look at this, there's no way you could cut it into a 2D slice and get the structural understanding of it, right? It is 3D and it needs 3D to be able to be understood. And we have been able to take this across all sorts of platforms. The one I wanted to, I'm hoping it's this. Something in the, I'm going to have to wait for this one to load. Yeah. Because I found on the web, I just hope that it does, a 1997 world of Tenochtitlan, Teotihuacan, that was built, the same book that I used to learn VRML, actually built this model, and it's still online. I'm going out, it looks like, to fetch it on the web. It hasn't loaded here yet. Let's see what I can do. Oh, yeah. I think I'll keep going. Give it a second. Okay, so we'll have to wait on that challenge. We'll see if I can let it cache itself while I'm navigating around here. And jump out to the last couple of slides. All right, so I've tried to make the case that, high performance, both computing and visualization, are really similar in the ways that we can kind of measure them by bandwidth and throughput. And the H in HCI, right, really means that we need to understand how the brain works, how perception works. Remember the color chips? If we can increase throughput just by changing a color scale, we should all be doing that. Right? It doesn't take any money. It doesn't take a new display investment. But the thing that has to happen, of course, is that these are measured by human performance on a task. Some tasks may really be very amenable to a certain kind of display, right? We've done a number of studies looking at the value of 3 screens or 4 screens or 1 screen. If you're doing a situational awareness task, if you're trying to judge distance, if you're trying to compare two values, right, in a 3D simulation. So the task is really important, and that's what we base all of our studies on. We have to consider the hardware platform, right? The Kinect is really cool for a lot of things, but my arms are gonna be tired at the end of the day if I have to do all my work like this, right? So it might be good for some things, might be bad for others. And of course the way that people approach the problem is really important in terms of how they're trained and what kind of metaphors they bring to the table. So I'm going to lay out the last couple of slides here, and I really see if we use this approach to structure how we run our usability studies, we're really trying to demonstrate the value of immersive technologies, how they increase the bandwidth, but also how 3D user interfaces can increase the throughput. And these are all based on human subject studies. We put people in the environment, we have them do real tasks. And one of the things that's really important, which the Teotihuacan and my Giza pyramids prove, is that reproducibility is one of the main criteria for progress in this field. Okay? We don't have hundreds of aviation simulation studies from the mid-80s and 90s because Silicon Graphics went bankrupt. And they were all written in proprietary Silicon Graphics stuff. So they were too big to fail. Eventually they did. And now, 20, 30 years later, science has stopped. Progress has stopped because I can't reproduce those experiments. I don't even know what they look like. couple of grainy black and white photos, right? That were done at like $300 per image. So reproducibility is really important for as we do these user studies in order to build the field and go forward. So there's a number of examples taking that same data and using it in lots of applications. 3D Blacksburg in our city model is one. We're bringing up GIS, SketchUp, multi-user collaborative worlds, all based on that same 3D model of our town. We've been able to bring sensor feeds into it. This is one last demo that I would like to do. But here's our webcams from our campus, right? So you can fly around the virtual campus and say, hi mom, or see if your friend is waiting for you at the library. These are all in the context of the 3D model. We're bringing in sensor data from the real world. And we're doing that with our streams, 3D Blacksburg, and with our Wi-Fi. You've seen this. This is the one that I might be able to run with the last minute, maybe if anybody's interested. But in this case, we were looking at a building on campus, which has a whole bunch of radios, access points. And through the web, in our 3D interface, we can pick those and see what's the activity, what's the bandwidth. I'm sorry, I'm overloading my terms here. But what are the frequencies that people are transmitting on and what power? So this is all exposing sensor data to the web. I'd love to show you that demo if we have time later. We've used this in our art center. So if you're trying to make the building smarter, maybe not smart is a good goal, but it will take a while. But here we're tracking people from in the physical world and reflecting that so that online people can come and participate in exhibitions and different kinds of interactive exhibits. So mirroring the events of the physical world to the virtual world. I mentioned the 3D print exchange. I really encourage people to go visit this. There's a lot of 3D right in the web. And we talked about standards and community. Okay, the last thing before I open it up, and I'd love to take some questions, is that we have an upcoming call for papers is published. Anybody's got some Web 3D that they want to introduce to the international community. Our 21st annual ACM conference is this year. So I encourage people to look at that, submit, or attend. Okay. So on time, is this good?
Yeah.
Okay. All right, great. Well, thank you. I'm happy to take some questions.